recording because if this is useful, somebody else might find. Okay, so if I go to Blackboard, that's very possible. Yeah. Okay, so let's say I'm in, are we the second or the first? We're the first, right? Okay, so I'm going to pretend, I'm going to push this button, pretend I'm a student. Then he says, how does he say to get to it? Tools, My Institution tab. Tools. You see it? Where? Oh. Okay, let's see. If I go to the February calendar, how do I go to the February calendar? Hey, look, it did. Look at this. Wow. Success. You know, that I wonder if there's a way I could make it post right to the site. I mean, right to where you log in, you see it instead of having to find it. Okay, so there's something about institutional. I don't know what these two are, but I guess I'm in multiple classes. So if I'm a student, it probably sees me as, here's the, what? The purple. Okay. And then it's, yeah, and then it should be 2 weeks on a 2-week rotating basis then. Yeah, I think I did it that way. Except spring break. Where did spring break come in? Is this spring break? No, or is this? Okay, so this is the spring break, I think. What? Create an event. Oh. Create an event. I can do stuff like that. Wow. Okay. So I'm going to exit the preview. Okay, it's taking an exit, taking its time. I'm going to go back to my Blackboard courses calendar. Well, there you go. And I was complaining about it all along. There it all is. See, I did all the classes at the same time. All right, so a successful video there. So you know what? I almost think I should stop that video and then restart it so that this could be, I think I'll do that. Well, now I'll just leave it there and we'll just go on. Yeah. So anyway, do what now? Yeah. Okay. So since I sort of hen scratched already on this, you know, I'm going to kind of go through this. What this is, and of course, I'm going to work this problem in a minute, but if you look back in the book, back around in here, he's deriving everything. And so what he does is he does this weird way of deriving. So he starts here and then out pops this. And it's okay, I guess. But for me, I like to see it a little bit more rigorous. So what we had done is we started the other day with this one, in which we showed that these two relations are basically the change. So if you think about it, the time derivative of the base vector that points in the r direction or out towards it is just theta dot times that. And what he's doing in the book, and I guess it's okay, but if you look in the book, it does it kind of like this. If you look at it, here's the base vector, this UR pointing out this way. And then an instant later, it moved a little bit. And so he's saying, okay, the change in R is pointing in the same direction as the theta And then he comes up and does this. So he's kind of getting you, what he's doing is he's saying, it's okay, believe me, this is what it is. And he shows a little vector, and it's just enough so you can believe him. And he is right. But on the other hand, what he's saying, the time derivative of the change in r is theta dot times the theta, the base vector in the theta. He should do that again with the other one, and I don't see it, but it's okay. So what we did is we did the same thing, but we showed it mathematically. So mathematically, those are true right there. The rate of change of the base vector pointing away is theta dot times the base vector that way. The change here points back towards the r, because if you think about it, if it moved like that, it's moving back towards the r. And so it's a minus times that. They're trying to sell me something. They're always trying to sell me something. Maybe it's a lottery ticket. Oh, I don't believe them. So what I did last time is I just took those two equations over, and I started over. I said r is equal to r, the length that changes as a function of time, times the base vector, which is a function of time as well. And then we did the product on it. We took, the derivative, time derivative of that vector is the time derivative of that times this plus that times the time derivative of that. So that I can go back here, just copy that down. I'm sorry, that's a mistake. No one told me. Fix. We must fix. That's supposed to be theta. So what we did is we took this, gave us this from, let's see if I can cut it from that equation. And so this is the same equation that sits over in the book right about right here. So if you look at it, it's the R is that one, the B theta is that one. If you look back, that's the same thing we have right here. Then the next thing is awful in that you're trying to take the time derivative of the velocity to give you the acceleration. So what do? You take the time derivative of this term times that one, plus that one times the time derivative here, plus time derivative of this one times these two, plus this one times the time derivative of that one times this one, plus this one and this one times the time derivative there. So the only oddities we have are these two, which we have to relate back over here, and we just copy them down. Okay, so this gets copied down. This one, since I'm now looking at it, this one gets copied right here. This one, okay, this one gets embedded in a couple of them. There's a square term here and this one. Then if you stare at them enough to recognize that you might have an R term here and an R term here, and you gather them here, you'll realize that you're gathering similar items here. You'll realize also that, believe it or not, these two repeat exactly the same thing, end up with a 2 down here. So when you're looking at this thing, you're thinking, oh my gosh, it's nauseating, it's huge. But in implementing it, it's pretty easy. So let's double check, look back at the book. And let's see, I think I can just do that. No, this. Select all. Trash can. You look at the acceleration, you see something like this. Oops. Where the R component is here, the theta component's here. Let's double check ourselves. R double dot minus R theta dot squared. R double dot r theta dot squared. And you come over and you see r theta dot plus 2 r dot theta dot. And you see r theta double dot 2 r dot theta dot. And that's where this comes from. Now, what do you have to do to implement it? It's not near as bad as it seems. It's just a lot of equations. And so what I did last time is I worked this problem. So I'm going to go over it real quick, and then I'm going to work another one. So here's a problem where they say, the collar is pinned and connected at B, so it slides along here, and this little rod goes, but it's going. Okay, let go of that thing, or I'll break it. This guide is something called a cardioid or something. And so there's an equation to it, kind of like a spirograph or something. So you just make this equation, it's all good. And then you slide it, but he tells you at 30 degrees, the angular velocity is that. So that's the speed of this rod. Determine the magnitude of the velocity of the collars at this point. Now, if you look back at the velocity, all you see that you need to know is r dot, r, and theta dot. R dot, r, and theta dot. This one you do need to know because he's probably going to tell you what the angle is. So it's implied that you need to know that one because you need to find this one at that angle, this one at that angle, and this one at that angle. And you put them into that equation, that gives you the equation. So the first thing you do, or first thing I did, is I just copied the R. And I said, okay, I copied it. Then he says, I need to find that, the R dot. And I'm like, oh, dr. But I don't have the R expressed as a function of time. I have it expressed as theta. So you do this little chain rule thing. You take that one, you realize, hey, that one is exactly this one. That's what he gave me. So I can just sort of copy it down. So what I did underneath there is I just copied it down. So, hey, I just take this one, copy it down here. Now I'm taking derivative. I hope I did this right. Minus, okay, now derivative of this is minus 2. Derivative cosine is minus sine. And there's your sine. And so you're done. So then I took this one, rearranged it a little bit, and put it in there. So this is the functional relationship, a value he gave us, another value he gave us, which he has to give you this one. He may give you this one in an equation. This one he has to tell you, because he can't just leave you on your own and say, I want you to find the velocity. Velocity at what point? In this case, it's 30 degrees. So believe it or not, now I need to find theta dot at 30 degrees, r at 30 degrees, r dot at 30 degrees, and plug it back in the equation, and that's it. So what I did is I took the equations, let's see, might be able to fit them all on the page. And the first thing I did is that this seems stupid. I want to know theta at 30 degrees. Well, it's just 30 degrees. That's a dumb, I don't even know why I did that. But theta dot at 30 degrees was given to me as 3. R at 30 degrees equals 2, and I put those numbers in, and I got that out a little bit. My handwriting's not great. I need to know R dot at 30. So I took that equation, put in the 3 that he told me, took the sine of 30, and I got that number. Now, all I do is I just go back and fill it out. I look up here, I read R dot, I read that one, I put it right here. I go up here and look at R, it's that one, times theta dot, which is that one, and then I multiply those two and I get this. We looked in the back of the book and it was minus 0.3 and 1.12, so turned out it was okay. That's all you're doing, you're just filling in, man. The next key, and this is something that he didn't ask, that I think is fairly important, is if I were to ask, so I did a little purple looking line right there, and then this is like a new problem. If someone came in and said, here's a vector, v, minus 0.3 ur, plus 1.12 u theta. Theta is 30. What is this number? And what is that number? And I'll tell you this, every single test I've ever given in dynamics for the last 2 years, I've done something like that. I don't tie it to the end of another problem, because if you mess up the calculation up above the purple line, then by nature, you're always going to get this wrong. If that's wrong, then this is going to be wrong. So there's no way, you can't disassociate those. So the way I generally do is I put something like this, say V is equal to that. Theta is equal to 30. What's I and J? Now, it turns out if you take the base vector like we did, there's 2 slides back where we looked at that. I have this UR. It's actually equal cosine theta I plus the sine theta J, being that. And then this is sine of theta, that part going backwards, and the cosine of theta J. This is what is commonly used throughout as just a simple transformation. This transformation exists pretty much everywhere when you're talking about transforming between 2 coordinate systems that are orthogonal and the base vectors are of length 1. So it's always the case. Now, if I give that problem, I generally give this somewhere on the page. The simplest thing to do is to come down and multiply this times minus 0.3 and this times minus 0.3. Multiply this times 1.12 and this times 1.12, and then add them, and you can fill in your numbers. And you're done. But then what I did is I said, well, now, if you want to do it differently, let's look at it another way. Another way is to write this as a matrix. One of the interesting properties of this matrix is that its inverse is the same thing as its transpose. Oh, and then what did I do? Where'd the rest of my notes go? They're gone. Well, anyway, that's weird. Let me try this. What did I just do? About F5. You know, I wonder if it got synced this morning. This morning when I logged in, it was having trouble. So it looks like my notes didn't get synced back over there. But, that's interesting. So on the YouTube lecture, you'll see more things here. But what you find out is if it's 30 degrees, I probably shouldn't waste my time here. But here, if you get like, call it T, it's degrees of 30. Is it showing up? It's not showing up. What's going on here? Okay, let me hit enter a couple times. What's going on here? Okay. Let's try this. Clear. Okay. Okay, we'll just start over. That was weird. I mean, it was right there. That I don't understand. Okay. This is kind of, I probably shouldn't even do this. Cosine degree 30. Sine degree, 30. And minus sine degree 30. Cosine. Ta-da. Oops. Did I do it? Watch this. Inverse. This is what I was talking about last time. It's always the same. It is the transpose of the one above it. And so it's easy. It's a standard. It's kind of something that's always occurs, which means it's easier to transfer from and to this But for lack of a better thing, I mean, if you were given this, I think at this point, I would just go and take this and multiply this equation times that, and this equation times that, and just add them up, you know. And that just gives you, well, that's really stinks. I don't like that. So, well, let's go back in and start working our problem. I don't know what happened there. That was stupid. Anyway, a peg is driven by a forked link, OA, along a path described by that equation right there, where R is in meters. When, okay, now, oops. Oh, come on. What's wrong with you? Okay, so here. Is it working? Yeah. So that, I think that's 90 degrees, but hey, we're going to use it as it is. The link has an angular velocity and an angular acceleration of that and that. Determine the radial transverse components of the peg's acceleration at that instant. Now, if you're looking back, there's two places we could find this. One is I could just copy that, or I could go over, but you know what? That's so compact and so quick. I think I'm just going to copy this one. What I'll do is trash can it and then just copy the little equation right there. You can't beat it as far as being compact. So there it is. So what I know is from looking at just this equation, I know that I need to know R, need to know R dot, a couple of R's, a couple of dots are. I see a theta dot and a theta double dot. Now, it doesn't, you don't see theta in here, but it's implied you're going to have it. So let's just, well, first of all, let's do the easiest thing first. I know these two. Radians per second squared. All right, we're good. This, however, is functionally this, e to the theta. What's R dot? Let's sort of monkey around with this a little bit. Maybe I'll do it over here. So dr dt equals to dr d theta. Oops, I pushed that button. Okay, go away. Go. What do these buttons do? Oh. Okay, go away. Hey, I didn't know. I could be typing stuff in that. Okay, what does this one do? Uh-oh. We don't want to do that. Okay, hopefully that goes away. What does this do? We don't want that. Close. We don't want that. Uh-oh. We don't want that. Okay, so the keyboard was useful. The other one was not. Your next screen press will be a right click. Oh, okay. So what does this one do? Ah, okay. Okay. Oh, okay. Oh, anyway, my palm of my hand hit that thing. Okay, d theta dt. So it's nothing more than theta dot times dr d theta. If I remember my math, what is that? Is that e theta? Isn't that? Isn't that what that is? It's supposed to be. Okay, so this kind of means that this one would be this. What would that next one be? Would it be this? Or is there something else, though? Is that it? Okay, let's think about that. Wait a minute. Is theta a constant? It's not. It varies with time, right? So let's see how we would do that. Let me scroll away. I'm sorry, scroll down. So how would we do dr dot dt? Okay, so if we wrote this in, it looks like this. So I think the first thing is I would have this like I had over there, e theta plus this. Wouldn't I have that? And see, I contend, maybe incorrectly, but I think I'm okay, that this since theta is a function of time, I have to do that. So I have to do this squared e to that. So I think it's that squared e to this. Just out of curiosity, let me roll forward up. I mean, it's the F1236. So you'll have to remember what that is when it's time to find the answer. So now what I need to do, I need to come over to right here, and I need to find r at theta equal pi over 4. I need to find r dot at theta equal pi over 4. I need to find r double dot at theta equal pi over 4. Okay. You would think this guy would do, but he's given me something that, okay, well, I can do this, but I'm not pleased about it. Okay, so okay, is it EXP? Is that the thing? Oh, yeah, I know that. Let's do this. EXP of 1. Yep, that's it. Okay, now over 4. So there's my first one. 2.1933. 2.1933. And any more digits I'm not interested in. Okay, now the next one is that number. Okay, so if you think about it, this number right here is right there. And as a result, that becomes 2 times 2.1933. Or, okay, where'd it go? Do that. 2 times that number, 4.3866. Okay. Now what I've got is I've got even something nastier. I've got 4, because I got to get this from here. I got to get that from here. Times 2.1933 plus 2 squared, 2.1933, which is the same thing as 4 plus be 8 times 2.1933. Is that right? I think that's it. 17.546. Okay. So I've got, what do I have? I've got my R, got my R dot, got my R double dot, got my theta, got my theta double dot. I can just fill it in now. So I move this just enough up there so I can read this equation. I can sort of, I'll just write it like they say. R double dot, which is 17. I'm basically saying the radial component 546 times theta double dot, which is 4 plus 2 times R dot, which is 4.3866. Okay. That's annoying enough. What did I just do? Us doing something wrong here. Okay. Okay, let's try this again. R double dot minus R, 2.1933. Theta dot squared, or 2 squared, gives me AR equaling to, okay, do that, minus 2.1933 times 4, 8.77773. Did I do that right? A theta, now I can go do this. Okay, 2.1933 times theta double dot 4 plus 2 R dot 4.3866 times theta dot of 2 becomes, okay, 1933 times, not minus, times 4 plus 2 times 2 times 4.3866 gives me 26.32. So if you want to write the acceleration as a vector, it'd be 8.773 UR plus 26.32 U theta. If I didn't goof up, that might be the answer. Let us see how bad I goofed up. Go down, go in size. Where'd it go? I think, I'm going to guess the answer is on page 702. Well, not there. But, uh-oh. Do you remember the number? Oh, 36. Okay, so something here looks, is it right? Oh, okay. Oh, I'm looking at, okay, so 8.77 was one of them. Okay, 8.77, I got that. 26.3. 26.3, all right. So it wasn't awful, only slightly. But really, when you look at what you're doing, yeah, there was a lot of derivation to come up with this thing. But as far as implementing, if you just go down and list, look in your set that you've got, and in this case, I'm doing the acceleration, so I have to know R dot, R double dot, theta dot, and theta double dot. If he only asks you for velocity, you don't need this one, and you don't need that one. All you need is R dot, and theta dot. And that's it. So, and then you're just going through the grind. And that's all there is to it. There's nothing more complex than that. The complexity might be how he does this or something like that. I'll show you one that's, awful. It's in the book, and it's very weird. But before I do that, does that seem okay? I mean, it isn't as bad as it seems unless you're working it, and unless you're stuck, and then if it seems bad for a bit. But if you can work your way through those kinks, then it's not that bad. Look at this awful one he's got here. Okay, wait. Okay, we were on page 80. Okay, no, we weren't on that page. Let's get rid of that. Okay. Oh, okay. You're probably right. Okay, here's the one I always like to look at. This one is not fun. Okay, so watch. Okay, so here's what you got. And it's, it makes sense if you really think about it. So a searchlight casts a spotlight along the face of a wall that's 100 meters from the searchlight. So here, so there it is. Determine the magnitudes of the velocity and acceleration at which the spot appears to travel across the wall. When that's the case, at 45, so he's got that being 45 right here. And then there's the speed. So that's if the little searchlight's going at a constant speed, like the airport light does, Yeah, exactly. So you look at it, and at first glance, you say, hey, wait a minute, how do you do this? Until he gives you this, okay, the polar coordinates are used to solve this problem since angular velocity. The necessary time derivative is first necessary to relate r to theta. And so he does that. And he does that through kind of this picture here. So you look at it, and at first glance, you're like, ooh, yeah. But then you realize, here's your r, here's your theta, and that's fixed. It's 100 meters. Yeah, 100 meters. So you're looking at that, and you're like, hey, wait a minute. Okay, r is a cosine. Oh, but wait a minute. The cosine goes underneath. Then he says, okay, you're sitting there and you have this relationship, right? Now, if it was sine or cosine, it would be a little bit less obnoxious, but now it's not, because you have to use the chain rule of calculus and noting that, and this is your r dot. Now, look at your r double dot. Oh, look at all that mess. Now, he doesn't do much except just sort of put it down there for you. But what you're doing is okay, so the first thing he did is he ran back here. He did that. And then, okay, so what happened is so he had this, r is equal to that. So then he did this, and then you have to carry your 100 anyway. So you get this with the d theta. Well, if you do that with dt under it, this with dt, you get that. Okay, then you do it again. So what's he do? He takes this, okay, but this is the derivative of that. So then you're like, wait a minute, I'm recopying this thing. Pretty soon you do this over and over. You have to do it how many times? 1 time, 2 times, and then 3. So there's your 1, there's your 2, there's your third. The last one's the easiest, where you're taking the time derivative on that. And so this is awful as far as, you would never get this on a test, because then it's a calculator competition, because who has the best calculator? Then of course I guess this is the simplified version of that. I guess because you have a theta dot squared here, some things like that, and you got 2 of these that you recombine to a third power. Then all you're doing, you think it's hard. The hardest part was right there. The rest of it's just plug and chug. Theta dot was 4. Theta's 45. So you stick that in there, okay? 45, 45. Okay, wait, yeah, 40, 45, 45, 4. 45, 4, 45, 45, and 4. Nope, that's not 4. This is 0. So you do that. Well, for the R, it's easier. You just put in 45. R dot, you get this, okay. For this R double dot, okay, 1600. Okay, good grief, I don't even know. Well, obviously one of these disappeared. Secant 45 tangent squared 45. Okay, maybe that is 0. No, it's right there. This is right here. Oh, he took this out. He took these two terms out, put here. Okay. So you just sort of go through this thing and you find out, I mean, it's awful, but it's not terrible in the sense of what you're doing. You're just simply, here, let's try and see if I can do this. Okay. You're just simply finding this value, and this value. You're finding this value, which is, okay, so you're finding R dot, R double dot. You're finding theta dot and theta double dot. Then you're just plugging them in. So you plug them in here. And of course, he has a component with the UR and a component with the U theta. He finds the square root and the squares. It turns out to be 800. And the acceleration's similar, but there's a little extra part. You put in R double dot minus R times theta dot squared. You just put it in right here. You put these in and you go through the process. So if you think about it, you got 6 numbers of which you really need 5 for the acceleration. For the velocity, you only need 3. And that's it. So the biggest part here was this mess. This part, if you were just given R dot and R theta, R double dot, you could just start plugging it in. And once you get all those, you get the numbers. So in the homework, there'll be a couple like that, and you just have to get your way through those, and then you realize it's not really that hard. And that's pretty much it. Now he's got some nice drawings here. As this thing went, you know, there's UR and there's U theta. There's the acceleration in the R. There's the acceleration in the theta, which together they make you run down the wall. I thought that was an intriguing problem, but it's also not for the calculus averse person. I mean, oh, are you? Okay. There is something else. I mean, this is way beside the point. This has nothing to do with anything, but I often do this so that people will be aware of it. There is a car called the Maxima. There is something else called Maxima. And look, it comes up in the first part of the system, not second. It is one of the original, you know, there's Mathematica, there's MATLAB, all these other things. This one was the first one. And I'll tell you a little story. I've worked in a lot of places, but one of the things I worked before was the Air Force Research Labs. And what was funny, when you go to work there, they have every piece of software in existence. And we were doing eigenvalues for electromagnetic propagation, which is a 6x6 symbolic eigenvalues thing. So it's a hard thing to do. None of the programs would work except this one. This one was the only one that would work. And it dates back, it's one of the earliest ones. And it's probably more stable than any of the others. And you just download it. And they're updating it fairly regular. You can see the latest update was in 2000, what is that, October 24th. And so I've used this before. It's a little bit quirky on the way you have to input and output things. Instead of a A is equal to, it's A colon equal to. That's how you assign things. So you get used to a little bit of that, and you find out you can do quite a bit of stuff on this thing. And it goes way back. It originated with a gentleman. Let's see if I can find the project. Okay, there should be. He was at University of Texas in Austin, and he passed away at some point, and they got permission to release this. That used to be, see, when I used it, it was called Maxima that way, M-A-C-S-Y-M-A. And for some reason, they renamed it when the government allowed them to release it freely. And so, very, very good package. And I'm trying to think of the guy's name. Here, let's see. Yeah, William. Yeah, there he is. 82. So he's the one that originally wrote this with, some other people have helped too, but he was basically, and then they wrote a thing to get it released, and the government said, okay, and it's a nice piece of software. So if you have to do something just overly complex, which you probably won't have to do while you're here, but if you do and you're out in a company and you see, oh my gosh, I can't get these things to work, this is something that might solve it, Yeah, there you go.
Did you enjoy working for the government?
Actually, it was a pretty good job. I really enjoyed it. I was around some really good people, and we did some nice work, and everybody just went in, we got it all done, and we went on. I mean, there was no fanfare, but it was good.